All right, welcome to the second section, I guess, to the review as far as like a first week for linear algebra here at Mount Vernon Online. This is the one set of videos I think most of my students probably need in terms of a review outside of using other resources or if they're meeting and working with other people outside of class. Or again, if you kind of randomly found this video, might be helpful just in terms of some basics, but it's really just the purpose. I do have a practice problem set for the online school up on Canvas, so make sure to take a look at that and work through those problems, see if you have any questions. There's a challenge question there too. I'll make a video talking about those problems and some of those problems, and I guess that'll be uploaded too as well, so you can kind of see how some of those worked out. To begin, when we talk about a matrix is a rectangular array of numbers. And so an array is an ordered list, so a vector is an array. And you can almost view a matrix as multiple vectors that are put together in terms of one rectangular space. This is an example of a matrix that is a 3x3 matrix. And what the 3x3 is referencing, as you can kind of tell, is that we have 3 rows and I have 3 columns. And so we could also refer to this as a square matrix, which a lot of the times we'll be working with square matrices. But we can also have matrices that aren't squared, that are more rectangular, thus the name. Because every square is a rectangle, but not the other way around. In general, when we talk about matrices, we kind of refer to those rows and columns using the letters M and N. The X or the cross there representing the dimensions. M rows by N columns, and that ultimately creates my matrix that we're dealing with. And so when I'm looking at this, it's really important to identify exactly which entries we want to reference. And so for example, if we're looking at this matrix and I want to identify the 5 in the middle, but I don't want to necessarily say 5. I want to be able to reference any matrix that I have, so some kind of generalized language. I could say there's no entry there, which will prove and things like that. We use the lowercase a, lowercase b, lowercase c, so lowercase letters, to represent the entries within a matrix. And on top of that, if I need to identify exactly its location, we identify it by its row and column, thus the whole order of the M and N. And to distinguish between the differences between those, to differentiate that, we use the letters I and J again. So not to be confused with the unit vectors. In this case, I and J just represent the ith row. I'll write that here, and the J column. So if you were looking at this matrix and you're like, okay, I want to talk about the number 6, I can reference that by saying, okay, that is in the 2nd row and in the 3rd column. So we read it top down, left to right. And so I would label that as A to 3 is equal to 6. That's what that entry is worth. When we start building out larger and larger matrices, if I want to now kind of think about this in terms of M and N, we can kind of start to see some, not patterns in terms of the indices, but you'll notice everything here would be in the 1st column, so J in all of these situations would be 1. And so you would have A11, A12, A13. Notice the rows, the I would stay the same, that number 1. The column, the 2nd entry would change, the second almost like an ordered pair. Notice the diagonals would all have the same numbers. So A11, A22, A23, which is going to be really important later on in terms of notations. In my notes, I kind of give a generalization for the matrix of size M by N, so you can kind of see with the dots and things like that. I'm not going to go through and write all that up on the board just to kind of save some time. But just in terms of notation and being aware of that, that's how we can discuss and talk about matrices. Another way that we can kind of write out matrices and discuss matrices is referencing entire rows or entire columns. And so if I have a general matrix A in terms of my notation, I could also think about this as the 1st column, the 2nd column, the 3rd column, and then if it goes all the way out to N, if we're working in this M by N space, the last column I would notate as AN. And then the lines aren't necessary. I like to use them to really reference trying to think of the word, I guess just the respective direction that we're going, the orientation, I guess might be the best word. I feel like there's another one that I just can't say kind of end of the day, but I can reference A1, A2, A3 as columns. I can also use a very similar numbering system to reference the rows. So I could also say the first row, the second row, the third row, and then this would go all the way down to the mth row, so M. Always kind of fun to say. And also describe a matrix using that notation as well. So just a couple of things to be familiar with. Primarily, we'll think about columns, but we could think about rows as well. And so working with the matrix, just be comfortable with this notation when you read it a little bit later. Now, in this first part, I also want to get into how we operate with matrices. And so I want to look at adding and subtracting because it's very intuitive, as well as scalar multiplication. And then in the second video, the second part, we will look at what's a little bit more complex and what may be a little bit weirder. But once you pick up on kind of the procedures and ideas, it kind of becomes very formulaic. It's how we multiply matrices together and how do we multiply a matrix and a vector together. And we've just got to be really, really careful if we can even do that multiplication. And so it'll be kind of key just to kind of watch out for. So in this one, I give two examples of matrices. I've got A is equal to 1, 3, and negative 2, 4. So just kind of reading across the rows. And then matrix B, I'm using 2, 5, 7, negative 1. And when we are adding matrices together, they have to be the same size. So when I'm looking at the dimensions, A in this case is a 2 by 2, B is a 2 by 2, so we can add these things together. So every entry has to have a corresponding entry, and just like with vectors, we can add them corresponding entries together. So my resultant matrix as my answer here, the first entry would be 1 plus 2 or 3. The second column in the first row, so my A or the 1, 2 entry, would be 3 plus 5 or 8. Negative 2 and 7, 4 and negative 1. And so here's my final answer. Here's my resultant matrix that we've created by addition. Now I can do the same thing with subtraction. So I can do A minus B. Again, works the same way, very, very similar to matrices. We could think about this as adding a negative, but since we haven't talked about scalars just yet, I'm just going to literally think about it in terms of subtraction. So I'm going to take my A11 and subtract off B11. So 1 minus 2 is negative 1. 3 minus 5 is negative 2. Negative 2 minus 7 is negative 9. 4 minus negative 1 is 5, giving me A minus B. Now, the big thing that we have to recognize, and it's the same thing when it comes to subtracting with numbers, is that this is not the same thing as saying B minus A. So I know when we looked at vectors and we were doing the subtraction, remember that the direction was different, the components were different. Therefore, the final answer would theoretically be different. It's not the same vector because it's not pointing in the same direction. And so it's the same thing when it comes down to matrices, working with addition and subtraction. Now, scalars, again, very quickly, because I think it's a very intuitive notion, works just like you would expect it to. Same thing as vectors. When I multiply a matrix by a scalar, every entry gets multiplied by that scalar. So the example I give again is something like 3 times A. So if this is still my matrix for A, I'm going to multiply every entry by 3. So I say, okay, well, 3 times 1 is 3, 9, negative 6, 12. And there's my final here. So much shorter in terms of talking about these topics, but just something to essentially outline. Because at its core, although it seems simple, things that we're going to have to be able to work with. We'll talk a little bit more about how matrices multiply together, and we'll get into some more semantics there. But that's it for the first part with matrices.